Hello and welcome to the Enamena video tutorial, Unit 6, Block 8, about reflectance measurements. My name is Stefanie Mayen. I work as optical engineer at the DLR in Spain with 5 years of working experience in the field of component qualification. My main field is reflectance measurements and infrared measurements, and also the development of new optical instruments and measurement methods. So today I will talk about reflectance measurements, and at first I will explain the relevance of reflectance for CSP applications, then the definitions of reflectance, then I will talk about measurement methods and evaluation, and about the cleanliness factor. And later there comes the summary. The reflectance is important in CSP applications because what happens on the solar collector is the first step in energy conversion chain, and the sunlight is reflected by the concentrator onto the absorber. So the reflectance of the solar irradiance spectrum is relevant, and this also includes the specular reflectance because, as we can see in the image, the sun disk has a diameter of about 10 milliradians, and the solar light that hits the collector is then reflected onto the absorber in the specular direction, and only what is reflected in this direction includes in the energy conversion chain. What goes out here will not be used in the concentrating system. So as we can see, the sun disk with a certain diameter is imaged by the concentrator on the absorber. And here, since the absorber, depending on the design, can be bigger than the image of the sun, there's a certain area where error is accepted. So if the specular property of the mirror or any other errors in the mirror at this point lead to diversion of the beam direction that hits, for example, a little bit on the side, the sunlight still is absorbed by the absorber, and therefore we have a certain area of acceptance for error, which is called the acceptance angle. And in typical Eurotrough parabolic collector designs, this is between 25 and 40 milliradians total angle. Because the reflectance characterizes the potential solar input, this is influenced also by possible soiling or degradation on the mirror, which can lead to a loss of reflectance, which then is also a loss in the power generation of the whole system. Reflectance is defined or can be separated into two parts. One is the specular reflectance, which refers to the reflected light that is reflected in the same outgoing angle as the incidence angle, where we have here the incidence light beam and then the specular reflected light beam, according to the law of reflectance, where incidence angle equals outgoing angle. This happens on perfectly flat surfaces, like mirrors. Then there's also the hemispherical reflectance, because if the surface is not perfectly flat, then the reflected light can be scattered into the whole hemisphere and not only in the specular direction. So the hemispherical reflectance describes the whole reflected light into the upper hemisphere. This can happen if the mirror surface becomes more diffuse by degradation or also by soiling. A typical solar mirror needs to have at least 90% of solar reflectance, and it of course needs to have good specularity, and those two properties must be stable over time in the outdoor exposure, because we don't want to have loss during the lifetime of the solar collector. So reflectance is defined as the ratio of reflected radiation to the incident radiation, and specularity describes the amount of reflected light in the specular direction, because only this is relevant for concentrating solar power technology. Reflectance depends on the wavelengths of the light, which is in our case the spectrum of the solar irradiance. Then it is also dependent on the incidence angle, which is the angle to the surface normal of the incident light beam. And then it is dependent on the acceptance angle, which is defined as a cutoff angle from the perfect specular direction to the angle where we still hit the absorber, even if the beam is a little bit off its perfect direction. So as symbolism, we always have to note those three components if we talk about reflectance. And so we write rho for reflectance, and then we define the wavelengths, the incidence angle, and the acceptance angle. If we talk about solar weighted reflectance, instead of the lambda for wavelengths, we put the symbol SW. The same for hemispherical reflectance with the index H. Since here no acceptance angle is necessary, we put in this position the H for hemispherical. Then we have the symbol G for the cleanliness factor, which I will talk about later. For reflectance measurements of the specular reflectance, there are several instruments that can be used. Typically in this area, we use, for example, the Devices and Services 15 reflectometer because it has proven to give repeatable measurements. It works where here the light source gives a light of 660 nanometer wavelength. Parallel light hits the sample, is reflected in the specular direction, and then passes an aperture where several aperture diameters can be selected that define the acceptance angle. Typically, the incidence angle is 15 degrees. And as the aperture angle, generally, it is recommended to use 12.5 milliradians acceptance angle, at least for parabolic draft technology. All reflectance measurements usually are taken in relative to a calibrated reference mirror. Because a lot of the specular reflectance measurement instruments can only measure at monochromatic wavelength intervals, it is important to measure the whole reflectance spectrum of the mirror material to do the solar weighting. So for this, for example, it can be used a spectrophotometer that is equipped with an integrating sphere, which needs to have a diameter of more or less 150 millimeter, or it can be bigger but should not be smaller. So the solar wavelength range is between 250 and 2500 nanometer, where it is relevant. So we do the measurement in this wavelength range at a measurement interval of 5 nanometer. Here also a typical incident angle is 8 degrees or also 15 degrees. And the same is here where the measurement is taken relative to a calibrated reference mirror. Here we have some exemplary data of typical solar mirror materials. We can see, for example, the blue curve is the spectrum of silvered glass mirror, which is a very stable, high reflectance. But depending on the thickness of the glass, there can happen some absorption by the glass. So we have also first surface mirrors like silvered polymer film, where we can see a higher reflectance over a great part of the spectrum. But in the UV range, there's a cutoff at a higher wavelength than other mirror materials. And we see so that this part of the solar radiation will not be reflected by this type of mirror. The green curve is a typical aluminium mirror, where we see here a dip in the solar to near infrared. That is material property of aluminium, which leads to a lower reflectance value. The yellow curve is the typical normalized solar spectrum. So we see that the important part is the visual, but it also goes to the near infrared. So if we have typical values for different kinds of mirror, we see that the solar weighted hemispherical reflectance of glass mirrors and polymer film are quite high, between 94 and 96%, depending on the glass thickness, where the aluminium is a little bit lower, which is due to the dip here in this part. Also, it can be seen that the specular reflectance for glass mirrors is the same as the hemispherical reflectance, which is due to the perfect flatness of those kinds of mirrors. But for aluminium and polymer film, we can see losses of 3 to 5% between specular and hemispherical reflectance. This can be seen here, for example, for the aluminium part. If we measure the specular reflectance, for example, at 660 nanometers, this would be this measurement value. And we see there's a lower value than the measured hemispherical reflectance. This also happens here at the polymer film. And this is proof that those materials have slightly rougher surface where part of the reflected light is lost outside of the measurement acceptance angle because it is scattered. This is relevant for the calculation of the solar-weighted specular reflectance because this ratio is supposed to be equal or similar over the whole spectrum. But it should be better to measure it, which is at the moment, at the current state of the art of instruments, not really possible. So for calculating the solar-weighted reflectance, we have to perform 2 steps. At first, we need to do a solar weighting of the whole hemispherical reflectance spectrum of the mirror with the normalized solar spectrum of the sun, where we recommend to use the solar standard ASTM G173 direct and circumsolar irradiation. To do this, we use this formula where basically the reflectance curve of the mirror is multiplied per wavelength by the solar irradiance, and then the whole is divided by the total sum of the irradiated solar energy, where the part of the solar irradiance also can be converted into weighting factors, which makes the process easier. Then we have the solar-weighted hemispherical reflectance, and this we can use to calculate the solar-weighted specular reflectance, where we remind ourselves that we only have the measurement at one wavelength. So we assume, as seen before in the graph, that the ratio between the specular reflectance at the measurement wavelength and the hemispherical reflectance at the same wavelength is constant over the whole spectrum, or at least similar. And so if we take this ratio, we only have to multiply it by the solar-weighted hemispherical reflectance, and then we get the solar-weighted specular reflectance. This procedure is only an approximation due to the fact that there's no reliable way to measure the specular reflectance spectrum over the range that we need at the current state of the art. This is what I talked about, was the procedure to evaluate a solar mirror material in the laboratory. But in a field of an actual solar power plant, it is important to monitor the reflectance of the mirrors over time, because this value is needed to evaluate the efficiency of the power plant, to evaluate degradation, and also to monitor the soiling rate. So for this, we use portable specular measurement instruments. In this case, the same as before, the devices and services reflectometer. It is always important to give the instrument some time to warm up and to accommodate to the surrounding conditions. Then the instrument is calibrated using the reference mirror with detector mode. And it is always important to do a beam centering on the mirror we want to measure, so that the reflected light beam is in the center of the measurement aperture. Then the measurement is performed, and at least 5 measurement spots should be averaged to get a reliable value. In the field, there are some challenges because the curvature of collector mirror must be taken into account by the alignment. So the display of this particular instruments should always be parallel to the longitudinal axis of curvature of the collector. Then changing ambient conditions can also lead to different values because of temperature drift. The same thing can happen if the battery status is low. So the instrument should not be standing in direct sunlight for a long time, for example. When measuring in the field, there are some challenges. For example, the curvature of parabolic collector mirror can lead to problems in the alignment. For example, at this particular instrument, it is important to have the display always aligned horizontally to the longitudinal axis of curvature, so that the area of the reflectance plane is parallel to this axis also. Then there can be changing ambient conditions that can lead to temperature drift, or even also a low battery status can lead to differences in measurement values. Therefore, it must be taken care, for example, to not leave the instrument in direct sunlight and to keep a good battery status. And because we have a small measurement area, if we measure a particularly dirty spot, this can also influence the measurement if the rest of the mirror is cleaner, for example. But talking about dirty mirrors, it is important to monitor the cleanliness of the mirrors, to know the particular efficiency of each day, and also evaluate the soiling rate over time to know when it is advisable to clean the mirrors. The cleanliness factor, G, is basically the ratio between the reflectance of a soiled mirror to clean mirror as a reference. To determine this value must be measured the mirror in a clean and also in a dirty state to monitor over time, as we can see here in this curve, where on a day with sandstorms, for example, or very dirty air, the reflectance can drop quite dramatically if the mirror gets dirty. This is very important because 1% of reflectance loss corresponds also to 1% loss of efficiency, which is the power output of the power plant. Because soiled mirrors lead to higher scattering, the measurement also becomes less repeatable, and therefore it is recommended to use the 46 milliradians aperture and also to do at least 5 or more measurements to get a reliable average value. So as a summary, we have learned that the specular mirror reflectance for CSP applications is relevant at an acceptance angle of 12.5 milliradians, which corresponds to an aperture diameter of 25 milliradians. This approximates the amount of useful energy in the whole system. For field measurements, the specular reflectance can be carried out using a portable reflectometer. Here, usually, we cannot measure the whole spectrum, but only particular wavelength ranges. For example, in this case, 660 nanometer. Therefore, for calculating the solar-weighted reflectance, we are using the solar spectrum and hemispherical reflectance data to calculate and convert specular reflectance measurements into the solar-weighted specular reflectance values. The ratio of the soil to the clean reflectance value characterizes the soiling rate or the cleanliness of the mirror, which is important for the efficiency evaluation of the power plant. And the whole process is documented in great detail as a reflectance measurement guideline, which can be downloaded at the SolarPaces homepage. So this is all about reflectance measurements. Thank you very much.